X-ray diffraction and X-ray crystallography are the last technique that you have to know for topic 21. This is an HL topic only. So X-ray crystallography uses the technique of X-ray diffraction. So this technique uses in-phase monochromatic X-rays being shown on a crystalline solid. So the word monochromatic just means that all the X-rays that are being used are of the same wavelength. The X-rays interact with the crystalline structure of the solid, and the X-rays are reflected back out of the solid. And because of the different atoms and bond lengths and bond angles that exist within that solid, the X-rays get reflected back out and create very unique patterns of interference with one another that can be detected because X-rays are fairly easy to detect with things like X-ray film. There are other things that can influence the pattern, such as the angle of incidence of the X-rays or the specific wavelength of X-rays that are used. But the basic principle is that you're shining X-rays on some sort of a solid, and because of the ways the X-rays interact with the crystalline structure of that solid, they get bounced out of the solid and create a pattern. So the X-rays do both constructive and destructive interference with one another. Constructive interference is where they add together and they create even stronger signals, whereas destructive interference is where the X-rays are passing out of the solid and their waves cancel one another out, and therefore they create nothing. So based on how the X-rays bounce off of atoms and bounce off of these crystals and then reflect out, they constructively and destructively interfere with themselves and create very interesting diffraction patterns. Okay? So the patterns can then be detected, analyzed, and some very complicated calculations applied to them, and they can give maps of electron density. And these maps can be used to identify certain atoms, since every type of atom has a unique electron configuration and electron density. A note that hydrogen does not show up in these maps because it only has one electron, and therefore its electron density is too low to really be detected here. But also these maps can help us visualize and measure actual bond angles and bond lengths that exist in molecules. So just another sort of schematic to help realize what's going on here. You take a crystalline solid, so it has to be solid, and it can't be amorphous like glass. That's not really an IB topic, crystalline versus amorphous solids, but just take my word for it. Most solids that we've talked about are crystalline. They have like a regular geometric structure to them when they're in the solid phase. You hit it with X-rays, which creates a very unique diffraction pattern. That pattern can be used to create electron density maps, which then can give us actual models, three-dimensional models. And so this right here is trying to show, it looks like a protein of some sort, possibly, what the 3D model that they take away from. So X-ray crystallography could be used on organic compounds. This is an example of the molecule anthracene, which has 3 benzene rings side by side. And this is an image that was created from X-ray crystallography showing an electron density map. And so you can clearly see the lines representing electron density around each carbon atom, right? You notice that the hydrogen atoms barely show up as these little sort of outer outlines. And you see that they form these nice regular hexagons, which we would predict, knowing that benzene has those delocalized electrons and the 6 even bond lengths, equal bond lengths. And so you could also measure the lengths between these dots, split it in half, and you'd have the atomic radii. The whole length would be a bond length, and the bond angle could easily be measured between 3 atoms, and you would see that it was about 120 degrees. All right, so just to reiterate some of those points, you could easily measure bond length, or you could measure bond angle like so, right? And you would measure the angle here. So there's lots of different things that you can actually do with these electron density maps once they're created. This is one of the most famous techniques in biochemistry because it was the technique that was used to help determine the famous double helix of DNA. This is an image of the X-ray crystallography, the X-ray diffraction that was created when this technique was used on a molecule of DNA, on a sample of DNA. It also gave evidence for the crystalline structure of NaCl, sodium chloride. That very regular crystal lattice produces this beautiful X-ray diffraction pattern. And it also gets used to help figure out the super complicated structures of the 3D structures of proteins. So what do you actually need to know? Because it is a fairly complicated technique and you could go into all sorts of depth about it, but really what you need to know for the IB is quite simple. X-ray diffraction is a useful analytical technique for analyzing the structures of crystalline solids. So I think it's important that you know this is only useful dealing with solids. Based on how the X-rays reflect off of atoms and interfere with each other, both constructively and destructively, the X-rays produce very unique diffraction patterns. And the diffraction patterns can be interpreted and analyzed to produce electron density maps and then models of 3D structures. And these maps can help show things like bond length and bond angles. From what I can tell, those are the key takeaways you need to know about X-ray diffraction slash crystallography. I'm not sure why I kept leaving out that word. We're going to add it in now. Slash crystallography. There we go.